So in this series of binary search, we will see what all variations of binary search are there, and we will try to cover some problems with which we will try to solve problems related to those variations, and you would learn how to use those variations, identify the patterns, and then you would be able to solve most of the problems of binary search. And let's look at this problem. This is a very interesting problem because this is not related to finding the exact position of element, or it is not related to checking whether an element is present or not in the array. It is related to finding the leftmost and the rightmost occurrence of an element in the array. And since the array is a sorted array, so such things can be done using binary search. So let's look at how to apply binary search in such a case. So I will start with the very simple situation. So you are given an array and you need to find whether a target element is present in that array or not. So how do you do in such cases? So basically you define your left index equal to 0 and you define right index is equal to array dot length minus 1, basically considering 0 based indexing. And what you do is while L left element is less than right element, so you calculate the mid. You say L plus R divided by 2 is what your mid is, and then there are three possibilities. Like whatever problem you're solving, there will be these three possibilities. Like in most of the cases, either your mid element is equal to a target element, or your mid element is greater than target element, or your mid element is less than target element, right? So based upon these three conditions, you reduce your search space. So initially your search space is starting from the left to the right of the array, right? And then you find some mid index, right, using this formula. And what do you do in such cases? If your current element, basically your element at index mid matches your target, you return true. Okay, element has been found, something else, like based upon the condition that is in the problem. And if your mid element is greater than target, so what do you do in such a case? So if your mid element is greater than target, so can you say that all the elements on the right side of mid will also be greater than the target, right? So this way what you can do is you can discard this much of your array, and you know that your mid element is also greater than the target, so you can discard the mid element itself also. So you say my search space will become this much, which is basically from left element, left position, to mid minus 1. So the way you do is you say, okay, my search space is going to be reduced here. I would set my mid, my right as mid minus 1. So your search space becomes in such a case. So if I copy this, when you are setting this element as R, the right element, so basically you have discarded this part, right? And when your mid element is less than the target, so this element is less than the target, so can you say all the elements on the left side of the array will also be less than the target? Yes, you can say, and you can discard that part. Even your mid element also is less than the target, so this is the part which you can discard. And how do you discard it? You basically set your left equal to mid plus 1, right? And now your loop will exit on the condition when your left is equal to right element, right? So there can be other you can check whether there are other edge cases or not, but the base edge case where our answer might be present is basically is this part. But when you are finding the exact elements, you can modify this condition. You just specify, okay, even if there is one element in the array, I will find the mid. So mid is basically equal to your left and R when your left is equal to right, and same thing happens. And either your left becomes greater than the right index, or you find it and you basically return from here, and outside the loop you return false, that I was not able to find that element in the array. So this is how you find the exact element in the array. And coming back to this problem, so there are two parts in this problem. One is to leftmost position, and the and one is rightmost position of that element, right? And so these are two different problems which are part of this problem, and there are two ways to calculate the mid. Let me tell you. So this is a very common way which people use to find the mid. Apart from this, there are two more ways. So basically you say left plus right minus left divide by 2, and other one is left plus r minus left divide by 2. So let's see quickly what is the difference between them. I will tell you in detail later which one to use and how do you know this. Let's say you have an array of length 3. So your index are basically 0, 1 and 2, and initially your left will be 0 and right will be 2, right? And if you find mid using this formula, so this will be basically 0 plus your right is 2 minus divided by 2, which becomes 1, right? And let's say if you are using this formula, what will be the mid with this? It will be 0 plus 2 minus 0 plus 1 divided by 2. This is basically 3 divided by 2. Integer division gives you 1 again, right? So no difference in cases where your array is of odd length. Let's consider array of even length. Let's say array of length 2, you have to index 0 and 1. So your left is 0 and your right is 1. And your mid using this formula, what it will be? This will be 0 plus 1 minus 0 divided by 2, which becomes 0, integer division, right? And let's look at this one. With this, what it becomes is 0 plus 1 minus 0. Now you are adding 1 from your side, 2, which is 2 divided by 2, which becomes 1. So with first algorithm, you end up on this one, and with the next formula, you end up on the right element. So since there are two elements in the array, you wouldn't know which one is the mid, and basically both can be mid, the left one on the right. This is right, left mid, right mid. So which one you should be using depends upon the problem statement, and within this problem statement we will see which to be used here. So let's say if I want to find the leftmost occurrence, so my array is like this one, and let's say my target element is t. It is coming, let's say 3 or 4 times, right? And for now, let's pick any one mid. I will pick this one for now, right? And you end up somewhere here with your mid. So there will be 3 possibilities once you have the mid. Either your array of mid is greater than target, or your array of mid is equal to target, right? Or your mid element is less than target, right? So when your mid element is equal to target, what can you say? Which part of your search space can you discard? Can you say that your answer wouldn't lie in the right part of the mid, because your mid itself is a target element? So either your mid is the leftmost position, or leftmost position lies on this part of the array. So basically this should be your new search space, because you know your answer lies in this part. So this is the part that you can discard. How will you discard this part? So basically you will say this is your RS index now, right? So in such a case you would say R is equal to mid. So see the difference there. When you were saying the target element, you were saying return, okay, I found the element. And when your element was greater than t, you were setting R equal to mid minus 1, right? Now in this scenario, you are saying, okay, I am discarding this part. So what is happening inside the while loop literally depends upon the kind of problem, or what your target is and what you are trying to find. And let's say this element, let's say if your mid was somewhere here. So if this element is greater than t, so which part can you discard? Can you say that all the elements on the right will also be greater than mid, because your array is sorted, right? And even your mid element is also greater than your target. So your answer lies in the left of the mid, right? So in such a case, you would say R is equal to mid minus 1, because you want to bring R here, and this will become your search space, right? And now third case, let's say you see that the mid element is less than t. So which part can you discard with it? Can you say that all the elements on the left of the mid are also less than t? Yes, you can say that, because it's a sorted array, and even your mid element is less than t. So your answer probably lies in the right part of the mid, in this part of the array. So here what you say is your left element, left index basically is mid plus 1. And now comes the termination condition. So this is what you do here, right? And one easy way to do is, like, instead of writing while loop like this, just write it like this, because whenever your left becomes right, basically you end up with just one element and it is there when you are exiting, right? And what you need to check here is so one thing which is still pending to be checked is that your element needs to be equal to the target, right? Because only then you would know, okay, that you have reached there. And when you're exiting from here, so there are two possibilities: either your index is one of the indexes out of the bound of array, or your index is at the position which you wanted to achieve. So a thumb rule is to use left index in such a cases. You can go into details like why left, why not right. I won't go into that depth in this video. Maybe I will create a separate video. But what you can do here is what you need to see. So left was initially the 0th index, and the only operation we are doing with the left is mid plus 1. So only way for left index to go out of array bound is it is going beyond this, right? So if you can use this condition that your left index should be less than the last index, or basically the length of the array, and your array of basically element at lth index should be equal to target, then you return left. Okay, I have found that position, the leftmost position. Otherwise you return -1, that I wasn't able to find it. Okay, and now looking at the edge case related to mid. So let's say we were left with just two elements, 4 and 5, and our target was 5, right? And you know, with two elements, this is your left, this is your right. And if you find the mid with the first algorithm, you end up on this one, right? And you see this array of mid is less than target. So you basically make this change, L is equal to mid plus 1. So you come here, and now your left is equal to right. You just exit from the array. And if you would have used another one, if you would have used this algorithm to calculate the mid, so you would end up on this one, 5, right? So you would see, array of mid is equal to the target, and you would do this, r is equal to mid. So basically r would stay here, and you would have end up in infinite loop, right? So whenever you are trying to find the leftmost part, or like smallest kind of thing, then you try to use this one where you are not adding an additional one inside, right? Basically where you are finding the leftmost mid, or wherever you are confused about which mid to use, you can just try with two elements, like what should be the behavior when you are left with just two elements. So let's write down the code for this part. This is what we will first recording. Let's write a function, find left index. You have array here, right? And you have target here. You define left and r, right? So what you say is, well, your left is less than r, and what exactly are we going to do is, what I will do is, okay, so this wouldn't compile. Let me bring it there so that while coding you don't need to think. All right, so you find mid this way with the first approach, L plus r minus L divided by 2, right? And you say if your array of mid is equal to target, what you do is you say r is equal to mid, else if array of mid is greater than t, you say r is equal to mid minus 1, else you basically say L is equal to mid plus 1, right? And now what we do is, if L is less than nums dot length and nums of L is equal to target, you return L, otherwise you return minus 1. So let's fix this part. So we have nums here, right? So this is what should suffice. We'll come back and test it. Now let's come to this part where we want to find the rightmost. Let me write it down here itself. So this is the representation of your array, and now there are a couple of cases possible. Again same, either your mid element is equal to target, or your mid element is less than target, or your mid element is greater than target. So when you are okay, let me say there are few positions where we have target. So when your mid element is equal to target, which part of the array can you discard when you are finding the rightmost element? If your mid element is target, so you know that your answer is either this mid index itself, or there can be more t's on the right side. So this is the part which you can discard, right? And how do you discard this part? You basically bring your left index here, so that your left and r represent this part of array. So in such a case, you say L is equal to mid, right? And if your current element is less than d, then again it's a similar case where your element is somewhere here. So you know your answer lies in the right part of the array. So you say left is equal to mid plus 1. And in this case, when your current element, the mid element, is greater than t, then you know that your answer doesn't lie in this part. Answer would be on the left side of the mid. So what you do is you set r is equal to mid minus 1, right? And now coming to this part, like so let me just copy this method, find left, we'll name it as right. Now coming to the part like which algorithm you should be selecting to use the mid. So again, let's consider this example 4 and 5. This is your left, this is your right? And this is where your leftmost element lies, the rightmost element lies, right? And in such a case, it will work fine. But now let's say this was the case, left and right. So if you find the mid with first algorithm in such a case, you will end up here. You will say, okay, my mid element is equal to target. So what you would basically do, you would set L is equal to mid, right? This is what you are gonna do. And nothing changes. You end up in a while loop, right? Infinite while loop. But if you find mid with the second formula, you will end up with mid on the right element. You would see, oh, it matches the target. And this is what you do. You change the L to your mid, and now your L becomes equal to R, and you are able to find the rightmost position. So let's modify this. I think a mistake ran in between. Sorry for that. So this part remains same. Again, this part remains same. So the way you are calculating the mid, this changes, right? And if your mid element is equal to target, what you do is you set L equal to R. Oh, it must be wrong there also, right? And if your mid element is greater than target, then you set R equal to mid minus 1, else you set L equal to mid plus 1, right? And this condition remains same. You would be always considering that your leftmost index is on your terminal position. All right, so let's try to run it. Return, to do is you call this method first, nums and target, and then you call the another method with it. Find right index is what you call, and the parameters remain same. Cool. So let's take a quick look. The leftmost index, passing nouns. All right, let's do a quick run for this. We run it. All right, so T is something it doesn't understand. I need to use target for it. Okay, so we have target there. Is there anything else we have? Okay, let's run it. All right, so cool, let's submit it. Oh, okay, so there is one index which is out of bound coming. So when you have just one element and your target is 0, so let's see where it would be breaking. So see, I found a mistake. So this is something which I was doing wrong. I forgot to subtract 1 from them. So that's why it is reducing, because L is 0 but R would be coming as 1 in such a case. Alright, cool, this worked. Alright, I hope you got some idea about which mid to be used where and what are the techniques to find the mid. And I will try to solve more problems and will share with you how to approach them so that you are able to solve the binary search problems. Cool, thank you for now.